Hey guys, welcome back to another episode of Structure Design to Eurocodes. If you missed the previous lectures, you can access them from the playlist called Structure Design to Eurocodes. There are 27 lectures to be uploaded, one each every Friday. So stay tuned in. Thanks for watching.
So what we're going to cover in this session on actions, combinations of actions, is very quickly, just a reminder of what's in Eurocode 0 and Eurocode 1. Then we're going to look at some definitions of actions. Not exciting at all, very dull, but very important as well, because these definitions get used over and over again. And there aren't that many of them, but they are completely critical. We'll have a very quick look through action calculation themselves, but I'm not going to dwell on it because you could spend a very long time going through it, but actually most of it is very similar to what we've already been doing to BS5400 or BD37, so it doesn't actually really merit a lot of time spent on it. But the combination of actions does, because that's quite different to what we've been doing before. So basically trying to concentrate really on the differences, not things which are very much the same as we used to do them. So just a very quick reminder of what's in these two documents, Eurocode 0 and Eurocode 1. Essentially, Eurocode 0, we need it because it defines all of these actions and gives the definitions, and also because it covers the combinations. It doesn't have anything to do with actual calculating actions, though. For that, we need Eurocode 1, and potentially we need the 10 parts. But for bridges, the last two, actions induced by cranes and machinery, actions in silos and tanks, isn't terribly relevant. So right, definitions. First very important definition is something called a characteristic value. And you remember earlier on I mentioned that K is used for a subscript for characteristic. It's not C, because C is used for concrete. So K is the next best thing, FK. And a characteristic value of an action is defined as a principal value with a fixed probability of being exceeded during a reference period. Now what that normally means is it's a 5% fractile value over a reference period equal to the design life. So if we show a probability distribution graph like that, the standard bell curve, then FK is basically up at the 5% fractile end. That's the formal definition. But a much better definition, or the realistic definition, is it's basically the action that you get when you go into Eurocode 1 and work it out. That's what you get as the default. You get the characteristic value. We then have a nominal value, and here you have to be a bit careful, because in old money, we used to talk about a nominal value as basically just being something that wasn't factored. So in fact, we actually used to call really what we now call a characteristic value, often a nominal value. A nominal value is distinct from a characteristic value in that it has nothing whatsoever to do with statistics. So nominal values normally apply to things like dead load, where you've just gone to the drawing, you've taken off the mean, the dimension of the slab, for example, that you've got on the drawing, and you've multiplied it by a mean density to get an unfactored nominal load. So nothing to do with probabilities. We then have something called a representative value, FREP. And this is the value of the action that you're actually going to use in the load combination. And we'll talk in the next slide about different values representative values can have. But the representative value takes into account two things, basically. It's used to take into account the fact that if you have lots of actions all applied together, they won't necessarily all be at their characteristic value at the same time. It just isn't going to happen on a sort of probability basis. You're not going to get wind and temperature and traffic all with their 5% fractile value for 120 years acting at the same time. So FREP basically takes account of that, and in combinations reduces the value of the loading that you actually use, or the action that you use. And the other time where you might want to reduce the value of an action from the characteristic value is if you're not considering a loading period equal to the life of the structure. So if you have something like a construction activity that's only going to last a few months, You don't want the 5% fractile with a return period of 120 years. You want something that's more realistic. And so sometimes you also choose an F-rep value where you're considering a time frame shorter than the full design life. So that might be construction. It also might be things like serviceability limit states. And you'll see why in a minute. Then finally, we have a design value. Oops, sorry, we have a design value. And the design value is basically the representative value multiplied by the load factor. And the load factor is gamma big F, and gamma big F is made up of gamma little f times gamma SD, where gamma SD is a partial factor to account for modelling uncertainties in a very much the same way as gamma F3 was used. The difference in the Eurocode is you will never see gamma SD because it's hidden in gamma big F. And the only reason you'd ever want to separate it out is if you're doing things like nonlinear analysis, where it does actually matter in which part of the process you put the different constituents. So if you're doing nonlinear analysis, you actually do want to put the modelling uncertainty factor in where you're modelling, and not on the loads. But generally, if you're not doing nonlinear analysis, you will only see gamma big F. That's all you get, and that's got gamma SD in it. So what can the representative values be that you use in calculations? Well, it could be the full characteristic value if the action you're considering is what's called a leading action, and we'll see that in a minute in the load combinations. So if I've got, for example, traffic and wind acting together, and traffic is going to produce a much bigger bending moment than wind is, then I would want to maximize the traffic loading. So I would take its full characteristic value in the combination. Sticking with that analogy, if I've got wind as well, wind is not going to have its full 5% fractile value at the same time, because that will not happen on probabilistic bases. So we need to reduce the value of wind in combination. And we do that by multiplying its full characteristic value that we've calculated from Eurocode 1 by a reduction factor, psi naught. And psi naught is called the combination factor. And that's given to you in Eurocode 0 and in the national annex to Eurocode 0, which varies that value in some situations. So that's generally, those two are really what you typically need for the ultimate limit state. Sometimes I might want what's called a frequent value, and this represents the value of an action that you might get with a return period of, say, a couple of months. So this might be relevant to construction, or more typically it's relevant to serviceability calculation when we're looking at crack widths. We're not necessarily interested in the worst crack that ever exists in the history of the structure. So if we want the frequent value, again, we always start with the characteristic value, but in this case we're multiplying by psi 1, which is the frequent factor, and that converts the full characteristic value down to something that's got a much shorter return period. And then finally we have what's called the quasi-permanent value of an action, which we obtain by multiplying the full characteristic value by psi 2. And psi 2 in Eurocode 0 or basically the quasi-permanent value in Eurocode 0 is defined as the value of action which will be exceeded about 50% of the time, but a much more sort of tangible definition, if you like, is it's an average value. So if you multiply the characteristic value by psi 2, what you're getting is pretty much an average. And that has some interesting effects, as we'll see throughout the course of the next day or so. But for example, psi 2 for traffic loading is 0. So that is saying that the average value of traffic that you see on a structure at any time is 0. That's really, it clearly probably isn't 0, but it's so small compared to the full characteristic value, it may as well be 0. And that has some very significant effects, because when we check crack widths for reinforced concrete, we check in the quasi-permanent combination, which means we check crack widths without any traffic. Having said that, temperature does have an average value. So the psi 2 value for temperature is, I think, 0.5, which means when we do crack width checks, we have to actually allow for temperature in the crack width check. So things are actually very different than the way they used to be, but in many ways much more logical. So this will be very quick, just looking through the actions, because they're relatively simple to do. Eurocode 1.1 deals with self-weights and loads for buildings. I'm not really going to concentrate on loads for buildings. There are a couple of slides here on that, but I'll just concentrate on really the self-weight calculation. So when we do self-weight, the characteristic value we use for self-weight is generally taken as the nominal value. So this is what we've done before. We just basically go to the drawing, we take off the thickness on the drawing for an element, and we multiply it by the average density given to us in Eurocode 1.1.1. Multiply the two together, that's our nominal self-weight. That also becomes the characteristic self-weight. So essentially on this bell curve again, we're designing in the middle here, we're not actually looking at variations in the thickness of the slab or in variations in the density. That will be taken into account in the gamma factors, generally. However, there are some exceptions. Where a loading has very, very marked variability, like surfacing, for example, so you've got very little control on surfacing. Even if it goes down in the new build the right thickness, there's a whole lifetime to consider, and it may be planed off so you've got less, it may be overlaid so you've got more. So in these situations, and the Eurocode defines loads that you need to consider in this way, you have to consider a lower bound and an upper bound value in your calculations. And so, for example, that covers bridge surfacing, it covers ballast on rail bridges, earth fill above culverts, and self-weight of cables and pipes. And for bridge surfacing, for example, you have to consider 40% more than the value on the drawings and 20% less. The load factor is then no different than the other load factors for dead load. So we don't have a massive load factor like 1.75 like we did previously. We have a standard load factor, but we have to consider upper bound and a lower bound. So we achieve the same thing, but a different way. The other thing to point out, which will be common for us for bridges, but is a change in practice for buildings designers in the UK, is that we apply, when we're factoring loads, we have a relieving gamma factor called gamma G inf standing for inferior, and we have an adverse gamma factor, gamma G sup standing for superior, and we have to decide whether the loading we're considering is overall adverse or relieving, and then apply the same gamma factor to the whole lot, the whole of the load. It is basically something called the single source principle. So if we're trying to work out what the bending moment at point A is, and we have dead load there, we have to decide whether the dead load unfactored is adverse or relieving at A. And if these spans are the same, then clearly it's adverse. And we factor everything up across both spans, even though this one here is a relieving span. And what we don't do is apply the adverse factor to this span and the relieving factor to the other span. Now, that's what we've just done in the past for bridges, but it's not what the buildings people have done, so it is quite a significant difference. There's one exception here. I'll just flag it up just in case you read it later on and think this is contrary to what I've just said. But basically you do factor separately quotes where the results of a verification are very sensitive to variations of the magnitude of a permanent action from place to place in the structure. And then it goes on to say the latter applies to verifications of static equilibrium and analogous limit states. Now basically it means if you've got things like uplift on a bearing or the whole structure can topple over, then you should factor the spans separately, but it does not apply to bending, shear, torsion. For things like that, you just factor in the way we've done before. So although this isn't very clear, it's probably slightly clearer than it was in BS 500, which said nothing at all about it. And a lot of engineers sort of did things like, if they were worried, then they did start factoring spans differently, and they did start applying gamma F3 to one span and not the other. At least this is clearer, even if not completely clear. These are, I'll skip over the loads for buildings because they're not really relevant to us, and jump straight into what we do for wind loading calculations, Eurocode 1.14. So that's basically just the contents. Most of what you have to do can be summed up by this diagram here, and it really is very, very similar to what we did previously in our code, and that's again because of the heavy presence the UK had on the drafting team. So basically we start off with our wind map, and our wind map is the same as it used to be. So we get our basic, we get our speed off the wind map. We then need to calculate a basic wind speed, and that basically involves introducing two coefficients to the speed we have on the wind map. One is a direction coefficient. So if we have statistical data on whether the wind blows more strongly in one direction than another, we can introduce a coefficient. and we have a season coefficient. So again, if we have data on particular seasons, the wind is stronger or weaker, again, we can use that. The National Annex has set both of those to 1, so we can't actually make any benefit from that. But if you're working in another country, then it may say something different in their National Annex. I think this is one thing that's worth bearing in mind. We're probably all sitting in the room thinking very much about working in the UK, and a lot of what we've put up has got the UK National Annex factors in it. But the whole point of the codes is to enable us to work elsewhere. So just be aware there is a real danger. If you start getting used to factors in your head that are from the UK National Annex, they won't be the same necessarily in another country. So we have to keep things general sometimes. So we've got a basic wind speed. We then need a mean wind speed, and this brings in basically height through roughness factor. And there's a separate factor called the orography factor. And I normally ask at this point whether everyone's heard the word orography. Sort of hands up. And God, did the hand go up? Bloody hell! Had to look it up. Yeah. I mean, I thought it was a typo when I first saw it, and I looked it up also in the Oxford Dictionary, and it says orography, sea topography. So it's just a classic example of somebody not drafting, I think, in their first language and picking a sort of second or third definition. But basically, this is an opportunity. If you've got, again, if you haven't modelled the effects of sort of hills in your isotachs right back at the start, then that's another opportunity to bring them in. But that's all modelled within the UK National Annex. So it's only the roughness factor which comes in there, which is just a function of altitude. Then where it goes slightly different from current British practice, but achieves the same thing, is that rather than now go on and calculate a pressure and then increase it for gust factors, we calculate we carry on with we take the basic mean wind speed in, we calculate what the basic pressure is, and then we increase it for a turbulence intensity factor. And the turbulence intensity factor is just basically, again, a function of height. And it's just how much the gusts increase with different levels. So at the end of that process, we get a gust pressure, and we then take the gust pressure, and if it's a bridge, then we'll apply a drag coefficient to calculate the overall force on a structure. If you're a buildings engineer, then they typically take the gust pressure and apply pressure coefficients, so you can design for forces on cladding in different parts of the structure. But we go down the drag coefficient route. And the next couple of slides, I think, will show typical drag coefficients, where they're almost identical to what we had previously in British codes. When we introduce the drag coefficient, we also introduce two more coefficients, CD and CS. CS is a size factor, which again was also wrapped up in BD 37. And this is just saying if you've got a very long structure or a very tall structure, it's very unlikely that all of the gusts will be in phase all the way up the structure, all the way along the structure. So for large structures, that's a reduction factor, just to take account of the fact that the gusts will not be in phase. And then there's a dynamics factor, which wasn't in BD 37. And this is if you're going down to low frequencies, sort of typically below 1 hertz, then you start running the risk that the gust pressures in here are not adequate for your design, because it may be that the natural frequencies in the gusts can actually be in phase with the structure, and that's not allowed in BD 37. BD 49, which covered aerodynamics, said if your natural frequency was less than 1 hertz, then you need to check turbulence response, and you need to go off and do a dynamic analysis. This is slightly more helpful, and it basically gives you some formulae to use in that situation for low frequencies where turbulence response is a problem. Well, that's really the only principal difference. And then you've got different drag factors, as I say, that again relate to width of deck over depth of deck. And if you put numbers into those, you'll find they're very, very similar to what we used to calculate. Temperature, again, you'll find this very, very similar. It all boils down to this diagram at the bottom of the slide, which is that you can represent a general temperature distribution as a uniform component, a vertically linearly varying component, and something that makes up the difference between that and where you started. So this residual component that doesn't have any net load effects on the structure. But one other component that the Eurocode introduces is a horizontal temperature variation, which we haven't previously had, and it works in a similar way to the vertical temperature profile, and it shouldn't be used on all structures. It's basically only really intended there for masts of things like cable stay bridges or very, very tall piers, where in the past we thought, well, there must be some differential temperature effect on this mast or pier because the sun's shining on one side, but there hasn't been anything in the code. So now that's covered in the code. So we work in exactly the same way. For differential temperature, we have different diagrams, and they are identical to the ones we used to have because they were put in by the UK delegate. So that's nice and simple. Horizontal temperature, there's something very similar there. It just basically tells you for different scenarios just a linear temperature to consider across the section. And the only other thing that the Eurocode introduces, which again won't affect the majority of designs, is in some situations we have to allow for a difference in the uniform temperature between different parts of the structure. So if you've got something like an arch bridge, again, in the past, people have sometimes thought, well, what happens if the deck is actually cooler than the arch rib because the arch is, the sun's on the arch? But there hasn't been anything in the code previously. So BD37, you would have kind of been within your rights to just put the same temperature on it, let the whole thing expand. Well, the Eurocode says in that sort of situation, then you should consider a difference in the uniform temperature. So you might actually have the arch rib 10 degrees hotter than the deck. But it's pretty well set out and prescriptive as to when you do and don't need to consider that. So for a normal bridge, yeah, you wouldn't need to consider any difference in temperature between the different components. So things are really the same as they were before. Traffic is quite different, but we will pick up traffic in more detail in the next talk. But I will introduce it here, just so we can get 2 bites at it. Gone are HA and HB, and in come various load models. So we have load models 1 to 4. I'll just say something very briefly about them now. But then we also have the old favourites like braking and acceleration, centrifugal, skidding, footwear and cycle track, and those loads are basically the same as they used to be. Load model 1 is the nearest equivalent to HA loading, but it looks very different. So load model 1 is made up of, in each lane, a tandem system, which is the vehicle, the 4-wheel vehicle that we can see up on the screen here, and it's also made up of a UDL. And the tandem system is a lot heavier than the equivalent knife edge load used to be in BD37, but the UDL is a lot lighter than the old HA UDL, and also it's constant with all loaded lengths, so it doesn't change with loaded length at all. So it's a lot simpler to use. In a similar sort of way as we had in BD37, each lane also has a lane factor which we apply, and that is a national annex determined parameter. So the basic loading that we have in lanes 1, 2 and 3, in lane 1 we have a tandem system vehicle with 2 300 kilonewton axles, in lane 2 a tandem system with 2 200 kilonewton axles, and in lane 3 a tandem system with 2 100 kilonewton axles. Together with that, in lanes 1, 2 and 3 we have a UDL, and this is a pressure per square metre, not per metre run, in the lane of 9 kilonewtons per square metre in lane 1, and then 2.5 in lanes 2 and 3. We'll also see in the next section, I'll briefly talk about how you split the deck up into lanes, but we have something called a remaining area. The remaining area is basically after you've split the deck up into the lanes the way it tells you to do, you may end up with something left. That's the remaining area. In the remaining area, we don't have any tandem systems. And in fact, for lanes above 3, we don't have a tandem system, but we do have some UDL to consider. Now, what's happened in the UK National Annex is we've selected lane factors, and they're separate for the tandem system. These are the alpha big Q values here, and for the UDL, the alpha little q factors here, and they look quite odd. So for the tandem system, all the lane factors are 1. So basically, we're just saying what the Eurocode's got is fine. We'll just stick with that. For the UDL, they're very odd-looking values. So in lane 1, we have 0.61, and in lane 2 and subsequent lanes, we have 2.2. And the reason for that is that if you multiply the lane factor by the UDL, as we're going to have to do when we apply the load, in lane 1, we get 0.61 times 9, which is a pressure of 5.5. And in lane 2, if we multiply 2.5 by 2.2, we get 5.5. So what we've done in the UK National Annex is end up transforming the UDL into a patch load. So we basically just decide what the adverse area of the deck is and just put a patch load across it. So it's very much simpler to do. That's not totally arbitrary. That's been done with calibration in mind. So with this loading here, calibrating load model 1 against the HA loading for a wide range of spans and a wide range of deck widths and lane widths, then generally the loading comes out within sort of plus or minus 10% of what it used to. And in many ways that's quite frustrating because it's a lot easier to put this loading on than it was in the old HA loading when we had to worry about cusp influence lines and all that sort of thing. So that's actually one area where things have got a bit simpler. When we actually start combining the loads together, though, things are a bit more complicated, I'm afraid. So, but that was the purpose of these rather curious-looking lane factors. Load model 2 is used really for local verification. So this is like the equivalent of the old single wheel load, and it's heavier because it's a 400 kilonewton axle. But because of the size of the wheel that you're applied to, the pressure actually comes out very similar to the pressure that we used to have. I think if you design with this local wheel load, it's slightly more onerous, if I'm honest, than the previous vehicle. But from again, the limited sort of calibration work that's been done, it doesn't sort of generally change structures. So if we used to design typical steel composites with sort of 16 mil bars or something transversely, it won't suddenly mean you need 20 bars, but it might mean the utilization is a bit higher, perhaps, in certain areas. Then we've got load models 3 and 4. Load model 3 is our special vehicles, and these are defined in the National Annex. So we don't have HB anymore. That's gone. That's not our special vehicle. In many ways, I think that's quite good because nobody actually really knew what an HB vehicle was anyway. So you design for sort of 45 HB, and then you get a heavy vessel, like a pressure vessel, coming along, and the client would say, well, is that 45 HB? And you have no idea. I'll have to check it for this specific vehicle. So what we've actually done is put in some vehicles which are more realistic of the sort of vehicles actually are on the network. And they're the SV vehicles, basically, we've been using anyway for assessment. The load model 4 is just crowd loading. I will go into actual combinations of how you combine different traffic loads together in the next section, so I won't cover that now, but basically you have to look at those different load models 1 to 4 in different combinations. So we don't have them all acting together, for example, but we might have the special vehicle with load model 1, which is the old equivalent of HB and HA, so there have to be some rules about how you add them together, and we'll cover that in the next session. So really, of all that lot, it's only really the traffic loading which is significantly different, and we'll pick that up, I say, specifically in the next section. What we need to do now is combinations, and this is different for those of you who particularly haven't seen it at all, but it's very different. We haven't got any load combinations tables for a start, so all you have is some formulae, and you have to basically apply generic formulae in turn until you get the worst overall answer. But what we're actually doing is the same as you were doing really in the load combination tables. There are 4 generic ULS combinations that we have to consider, and that these are nothing to do with whether like wind is the leading action or traffic is the leading action or temperature. They're generic. It's more about what you're trying to achieve. So the persistent load combination, for example, represents normal day-to-day usage of the structure. And that's really the combination you'll typically be doing the design in, and it's likely to be the governing combination for the design. We have something called a transient combination, and this is really picking up on things like construction, where if you have loadings with a shorter term duration, you might want to consider them in the transient combination so that you can reduce their impact from the full characteristic values. But equally, you might just be conservative and take it in the persistent combination. I think where things are very different from previous British practices, we have specifically separate combinations for accidental and seismic. And seismic's clearly not a great deal of relevance to us here, but it would be if you go overseas. And if you've got, if you're a buildings designer, if you've got fire, if you're a bridge designer and you've got impact from a road vehicle or ship impact, you do these combinations, you do that particular case in the accidental combination, and it's a different formulation to the others, and you'll see why in a minute. That's just a quick reminder of the different types of representative values that we'll be looking at in the combinations. So what I'll do is I'll just jump straight into the persistent combination, which is to say is normal design conditions during service life. And this is basically our load combination expression. This is what we have to do to determine load effects in the future. And it looks horrendous if it's the first time you've seen it. But actually it's not too difficult in its application. What this is saying is I need to find the E, the effect of all of these actions in the brackets. And that effect might be a bending moment, if that's what I'm looking at, or it might be a shear, it might be a torsion. And what this is saying is if I'm going to put loads onto a structure, let's first of all consider dead load, or the permanent actions. So I need to first of all identify all of the permanent actions on my structure, which might be the surfacing, the weights of the parapet, dead loads from the structural concrete, structural steel. So I need to get all of those values from Eurocode 1, with the GK, G standing for gravity, K standing for characteristic, because I haven't factored it yet. And I need to multiply each of those components by its respective gamma factor. And then I add them all up, hence the big sigma sign at the end. So that's exactly what I would have done previously to BD37. Worked out my dead loads, factored them, put them on the model together. If you've got any external pre-stress, then again we take the pre-stressing force and we multiply it by its gamma factor for pre-stressing, and we add that onto the effects of the dead load. Where it kind of departs, I guess, from the load combination approach, table approach, is you then need to identify your leading action. And more often than not, this will be pretty obvious what it actually is. So if you're designing a normal piece of reinforced concrete, normal sort of bridge, typically it's just going to be the traffic loading, which is going to produce the biggest bending moment. So whatever's going to do the biggest effect, that's what you typically choose as your first go at a leading action. And in the same way as we typically know load combination 1 will govern particular structures, this is just the same. We're just saying we know that traffic's going to be the leading action generally. So we calculate the traffic action, we multiply by its full gamma factor, and that's our factored leading action. We then have to consider everything else that we haven't considered to date on the variable actions side. So that might be things like temperature, wind, snow. For each of these within reason, we need to calculate the characteristic value. We need to multiply by the combination value, which reduces its magnitude because of the probabilistic low probability of it reaching its peak value at the same time. And then we factor by the gamma factor for variable actions. And the important thing with doing this is the gamma factor always stays the same. It doesn't keep changing indifferently whether something's leading or not leading. The gamma factor always stays the same. Where you make the reduction to the loading at the ultimate limit state is always with these combination factors, not the gamma factor. That's a very significant change. There's a slide coming up, but the Eurocode basically gives you some exceptions. So clearly it would be a complete pain in the backside to have to consider everything else that you haven't considered. So there are general get-outs, like you never consider wind and temperature together. And that's really, again, the same as we did before. And you generally don't need to consider snow at the same time as traffic loading, because you can't drive in a lot of snow, fairly obviously. So actually, although this looks like you've got to consider everything together, actually what you do need to consider together is relatively small because of the exceptions. And having worked that out, you then need to consider other things as the leading action, just make sure there's nothing else more critical. As I say, in the same way as we tend to know which combinations will govern in BD37, the same thing happens here. So I mean, how many times do we actually, for a sort of RC deck, do we actually plough through all the combinations, to check what the bending moment is in the vertical direction? We generally don't, because we know what's going to govern. I won't go through the two equivalent versions that have popped up there, because you're only allowed to do those for buildings. You're not allowed to do them for bridges. But the significance there is that they've gone a step further and said, well, if you have full factored dead load, then it's actually starting to get quite remote as a possibility to have fully factored leading action as well. So I'm actually going to make my leading action slightly reduced. But if I do that to my leading action, I need to consider another version where I have a fully factored leading action and slightly make a reduction to the dead load. So that's just for info. You mustn't do that for bridges. But beware of buildings designers trampling on our territory, because they may well come and do that by mistake. That's one of the things with Eurocodes, is it's great in the sense that it allows you to move between buildings and bridges much more frequently, but the same old dangers still remain that we had before, and that you get in your head a certain way of doing it and think it will be the same in the other discipline, and it might not be. So you have to be a bit careful. For the accidental combination, then we have to check two situations. Basically, we have to check during the accident and then after the accident in the sort of damaged, potentially damaged condition, if that's the way we've designed it to be, to end up with some damage. And the first thing to note here is that in the accidental situation, there are no gamma factors on anything. And the reason for that is we're not expecting the structure to be sort of completely serviceable after an impact. We're expecting to have to actually do some remedials to it, but we don't want it to collapse. But the format's still basically the same, so we sum up all the dead loads, had any pre-stress. The accidental action itself becomes effectively the leading action, so that might be impact on a bridge pier or ship impact. And then we have a series of other actions which we have to consider. There's a next sort of ranking leading action where we use the frequent combination. So for a typical bridge deck, if we've got an impact on a bridge pier, the load we have on the deck at the time is the frequent value. So we take the full traffic loading and reduce it by the frequent factor. Everything else then has its quasi-permanent value. So that's basically average values of any other variable actions. So that's during the impact. After impact, depending how we've designed it, we might have designed it with a plastic global analysis because that's allowed in the Eurocode. So you might actually have a column that's now leaning over at a certain degree because of the energy it's absorbed. In that situation, the actual impact has gone away, but we've got to make sure the thing can still stand up in its damaged configuration. So in that particular situation, we take a leading action with its frequent value again and average values of everything else. So the leading action would typically be the traffic again with a frequent value, and all that's saying, say frequent value being something the worst case in a matter of a few months. All that's saying is that we can't shut the bridge instantaneously. After an impact, the traffic will still be flowing on the bridge above for a finite period of time until we come and intervene and either close the bridge or give it a clean bill of health and say the traffic can stay on there. So we need to have something there, but not the full magnitude. And seismic is really a special version of the accidental combination, if you like. Again, there are no load factors there. The seismic action is the leading action, and for seismic, all other variable actions, including traffic, have their quasi-permanent values. So for seismic events, Psi2 for traffic loading is 0, so we don't have traffic on the bridge in a seismic event. So that's ULS. Serviceability similarly has 3 generic combinations. Yep.
Just to have an imagination, what are typical values for frequent and frequent?
You'll see in a minute. I'll put some up in a minute.
What's 07 and 05?
I'll show you in a minute, yeah. Rather than me trying to remember them, I'll show you in a minute. Serviceability, we have 3, again, generic combinations, and these are absolutely critical because different serviceability checks are done in different combinations. Quasi-permanent is the least onerous, rising up through frequent to the characteristic, the most onerous. So, I mean, the simplest way to illustrate this is just with a piece of reinforced concrete. So if you've got a reinforced concrete bridge, a load moves across it, traffic moves across it, a crack opens and shuts as the vehicle goes away. The question is, does that matter at all to durability if the crack opens and shuts? And the view that the Eurocode 2 project team have taken, and it's supported by a lot of test evidence, is that no, it doesn't really matter. It's not the biggest crack that ever exists in the life of the structure that's important to durability. It's more the average crack that's open that lets the contaminants in. So when we do crack width checks for reinforced concrete, we use the quasi-permanent combination, which is basically average loading. And as I said, the significance of that is that traffic loading for highway bridges is 0, but we do have to consider temperature. At the other end of the scale, same piece of reinforced concrete, same bridge, whatever, same load moves across it, and all the reinforcement yields as the vehicle goes across. Well, you can't have that ever happen because it won't recover. It will stay permanently deformed, permanent damage. So when you check stresses in reinforcement and also stresses in concrete, we have to use the characteristic combination because we can't have those irreversible damage states occur any time during the life of the structure. So the characteristic combination, as it sounds, is the worst, basically the worst case serviceability loading in the lifetime of the structure. And then in between the two, you have something which is basically in between the two, so that the frequent combination represents the worst sort of loading you're going to get in a matter of a couple of months. And for serviceability combinations, that's generally used for pre-stress checks, for checking crack widths in pre-stress. And that's only because people get historically more worried about cracks in pre-stress because of the potential greater damage to pre-stress structures corroding. And the serviceability combinations look very similar to the ultimate limit state one. So the characteristic combination is basically the same as the ULS persistent combination, but without the gamma factors. And then the frequent combination has the leading action reduced by the frequent factor, and the quasi-permanent combination has all of the variable actions reduced by the quasi-permanent factor. These are basically the values, or typical values that we have for the various different psi factors. So you see, for example, for quasi-permanent, for average, everything's 0 with the exception of thermal actions. So the average thermal effect is 50% of the full characteristic effect. The combination values, psi naught, you can see things like the tandem system has 75% of its full value, pedestrians 40%, and those values are basically sort of mirrored in the frequent values there as well. So you don't. The key point really is you don't need to make up these values. You take them straight out of the national annex of the country that you're working in. And the UK values, these are actually the recommended values rather than UK values. When we look at live load in the next session, we'll be using the UK values, but they're pretty much the same. Other than the UDL in the load model 1, we've made the same as for the tandem systems, and they're both 0.75. These are the exceptions I mentioned about not having to combine everything together. So the exceptions are given in Eurocode in all Annex A2. And so we get things like snow needn't be considered with traffic loading, wind and thermal needn't be combined together, wind need not be combined with an accidental action. There was some argument about that, particularly when you come to ship impact. You might, in your mind, you might sort of first of all think, well, when is a ship most likely to impact a structure? Probably when it's very windy. And there's a lot looked at that, and in the end, it was decided no, we'll stick with not combining the two together. And the reason is when you start investigating ship impacts, wind as a cause is actually quite a long way down. Now, the most common cause of ship impact is mechanical failure of steerage. I think the second is the crew being pissed. And actually wind comes quite a long way down, and even when you do have wind together with the impact, if you think about the relative magnitudes of a ship whacking into a pier and a bit of wind on the structure, well, you can kind of forget the wind. So it does actually kind of stack up. So although it looks a bit curious to start with, it does actually work. These are the partial factors, which are the default, the recommended values. The UK tweaks them slightly, but generally the variable actions are exactly as here. Traffic is a value at gamma factor of 1.35. All other variable actions, temperature and wind, have a gamma factor of 1.5. In the Eurocode, the recommended position, which most countries seem to have adopted, I think, is that all dead loads have 1.35. Well, in the UK, we've sort of tweaked them back to where they were before. So we thought that 1.35 was too onerous for steel. It doesn't really matter so much for steel composite, a bit more steel weight, because the steel weight's relatively small. But if you go to things like steel orthotropic box girders, which are designed to be light, then actually having a gamma factor of 1.35 completely defeats the point of having gone for a light structure. So that for steel, that's been sort of reduced back down to a value that was more akin to what we had in BD 37. So what we finish with here is just a quick example of how it actually works in practice. This is a typical steel composite bridge. Steel composite was just chosen for lots of actions, really, to combine together. And the purpose is just to determine the maximum bending moment at some point in the span. So what we've started with here basically an engineer has first of all had to go and work out all of the different types of action on the structure in the same way as we would do now. So under self-weight, we've got things like the steel self-weight, we've got the concrete, the surfacing, we've got other permanent loads like the verge, the parapets and the settlement. Shrinkage is in there as well as a permanent load. And then we have the variable actions, which are your temperature, wind, traffic, vehicle impact, and seismic as well. So the first thing that the engineer will have to do is go to Eurocode 1 and calculate all of those actions. And then you'd analyse for each of those actions and work out, in this particular case, a characteristic bending moment. So we haven't done any of that combinations yet. We've just taken the wind force, for example, from Eurocode 1 and applied it to the structure, and that gives us a bending moment, MEK. And you'll see here in this format there's two columns, an upper value and a lower value. And they're all the same with the exception of surfacing. And that just comes back to what I was saying, that if your load type has a lot of variability, and surfacing is one of those ones that comes in that category, then you have to consider an upper bound and a lower bound in your unfactored loads to start with. Otherwise they're all the same. In this sort of spreadsheet type format, somebody's then filled in from, these are recommended values, but you do the same for the national annex, the unfavourable values and the favourable values of the gamma factors. And they've also filled in all the combination factors, psi0, psi1 and psi2, again, from the Eurocode. So that's basically all the data in there, but we then need to use that data to perform different load combinations. So if we're interested in the biggest bending moment in the ultimate limit state combination, then the formulation at the bottom of the screen there is the one we've got to use to calculate what the bending moment is. So the first thing to note with that formulation is it's a persistent combination. It's not an accidental combination, so we're not interested in vehicle impact. In fact, there isn't any effect here to consider anyway, but if there was, we wouldn't be considering this in the persistent combination. And it's not a seismic combination either, so we're also not interested in the seismic action in this combination. So we can just cross those out. So then we start at the left-hand end of the formula and looking at the dead loads. So I want to maximise the dead load, so I choose all the upper bound values of dead load, and I multiply those by the unfavourable gamma factor, and I multiply all those numbers together, and they appear on the right-hand side as the design action effects. Looking at the second term, there isn't any pre-stress, so I don't need to do anything there. We need to now identify a leading action in the third term. And looking at what we've got temperature, wind and traffic. Traffic is quite a lot bigger with a 12.5 meganewton meter bending moment than any of the other effects, so it's reasonable to take that as the leading action. So we then multiply that by its full gamma factor, and there is no other combination factor to multiply by. In this example, there's just a factorial unity factor there. We could have just omitted it. And that gives us our design bending moment from traffic. Now we need to work on the last part of the combination. So this is all the leftovers. And we've got wind and temperature left. Temperature is the biggest of the remaining ones. So if we start with temperature, what we need to do is highlight temperature. We need to multiply by the gamma factor for temperature, 1.5. But then we need to multiply by the combination factor, psi0, to take account of the fact that we won't get full temperature at the same time as full traffic. And that factor is 0.6, and so at the end of that we multiply the three numbers together and we get a design bending moment from the temperature. And then the last variable action we have is wind, so we should do exactly the same process for wind, but we can come back to the overarching principle that we don't need to consider temperature and wind together. So I can just ignore wind. Be conservative if I used it, I can just ignore wind. So that gives us a value of 0. So then basically all we do is add up all of that and we get a design bending moment at the end of it of 36.1 meganewton meters. So that kind of wraps it up really. I mean, there is a lot of new definition in there. It is quite different, but it's very logical once you get your head around it, because you can actually see what you're doing with these combinations rather than things being hidden away in a gamma factor. So it's quite logical. It lends itself to analysing a much broader range of structures. So quite often it was with complicated structures, it was actually quite difficult to know how to apply the combinations for in BD37. If you had a cable stayed bridge and you had sort of pylons and you had temperature on the side of the pylons, it actually got quite difficult. What combination are we now using? So it's a much better framework for doing things. And there is quite a lot of positive stuff about it. So I mean, most of the load calculation is very similar to what we did before. The traffic is very different, but again, with a bit of practice, it's actually quite simple in many ways. It's actually simpler to apply to the structure. And with that sort of patch loading, you can, in many situations, you can go back to just like eyeing up where to put the load on a structure rather than having to generate lots of influence lines to precisely calculate the loaded length. So it's quite a lot of positives there. So things are different, but they're not really more difficult. But they will be clearly to start with until you actually get into it. But once you've got some practice, things will not be too difficult.